another section that we're going to cover today. It's the inverse trigonometric functions and their integration. Again, we've talked about the derivative of the arc sine, 1 over the square root of 1 minus x squared, or the arc cosine with minus 1 over the square root of 1 minus x squared. So when we look at the antiderivative that ends up giving me these functions, we have these three now additional formulas. Three more formulas to be aware of. If you have a square root of a number squared minus a function squared, and you have the proper du for this u, then the integral of a integral that looks like this is the arc sine of u over a plus c. See example A here. See the square root? Okay. When we have a square root, we're looking at rules that have square roots in them. This is one of them that has it. It's got to be a number minus a function squared. And we have that. We have a number, and any number is squared. So this is 2 squared. So a is 2. X squared. So u is x. And the derivative of x is dx. So this does match du over a squared minus u squared. So once we've matched it up, I can just write the answer. That is the arc sine of u, and our u is x, over a, our a was 2, so the arc sine of x over 2 plus c. A second one that yields us an inverse trig function is when we have denominator again. Very few things have denominators. So you have a denominator, 2 terms. A number, any number is a number squared, so a number squared plus a function squared. The derivative of u is du, so we have the right du for all of this. Then this is the integral of 1 over a, whatever a was here, the arctan of u over a. And looking at example B here, we've got a number denominator, a number squared plus a function squared. The number is 2, and the square root of 2 is 2. The square root of 2 squared is 2, so that we have a number squared. And this is the function. It's 3x squared. But the du of 3x is going to be 3 dx. So I need a 3 dx to have the proper du. And if I multiply by 3, I've got to divide by 3. But now I've got a number squared plus a function squared in the denominator. A number squared plus a function squared in the denominator. I have the proper du for it. And so it's going to be 1/3 is going to go for the ride. 1 over a is the square root of 2. So 1 over 3, the square root of 2, arctan of u, 3x, over a, square root of 2 plus c. And the third one, and only the other one that has a square root in it, if you have a square root, and in the square root is a function squared minus a number squared, and you have whatever u was multiplied outside times the square root, and you have the proper du. If you have it looking just like that, then the integral is 1 over a, the arc sine of the absolute value of u, over a plus c. So you have to have the absolute value there. So again, if you look at example C, we have a square root. And we only have 2 rules that have square roots in it. And the number minus the function. Well, the numbers, it's not. Well, we have another one that says a function squared minus a number squared. So let's see. Oh, that's a function squared. It's 2x squared. That's the number squared. That's 3 squared. So I have the proper piece there. If u is 2x, du is 2 dx, so I need a 2 up top. And if I have a 2 up top, I need to have a 2 at the bottom. And now I have the u, because u is 2x. So I have 2x, the square root of 2x squared minus 3 squared. And I have the proper du, 2 dx, so this matches. So it's 1 over a, A is 3, so it's 1/3 the arctan of the absolute value of u, 2x, over a plus c. So the integrals in those examples are fairly straightforward in the application of integral formulas, okay? But sometimes it doesn't look that easy, and we have to realize that they run around disguised a little bit sometimes. So we need to be able to sense what we have. So here is an integral with a square root. Well, we have an integral with a square root. I only have two possibilities. I have to have a function squared, though, in either of the possibilities. And so if I let u be e to the x, then this is e to the x squared. And then du would be e to the x dx. That would be our result. So dx would be du over e to the x, du over u. So now we substitute, right? We got dx, square root of, and we now have e to the x squared minus 1. So we've got a function minus a number squared. Dx is du over u. So in that case, we're going to end up with, right, if u is e to the x, we've got u squared minus 1. Dx is du over u, which gives me u, the square root of u squared minus 1 dx, which matches our formula. We have a function squared minus a number squared inside a square root multiplied by the u and the proper du. So that's arcsecant. So it's 1 over u, 1 over a is 1, so 1 over a is 1. The absolute value of u over a plus c, so this is the arcsecant of e to the x plus c. How we get the result. Another example. Well, back when we started doing integrals, we said we cannot do integrals that have a sum in the numerator. But since this is a square root, I don't care the stuff inside, this is a single term in the denominator, so I can rewrite this as x over the square root of 4 minus x squared. And I can write this as 2 over the square root of 4 minus x squared. U, let u be 4 minus x squared, and we have a du that fits it. And this looks like arc sine. And I'll rewrite this up for you in a pincast to give you the whole steps, step by step on some of these. Now, one of the big tools in integration is one of those things that you didn't really like along the way, but completing the square. If we have a quadratic, we have a square term and a linear term and a constant term. We can take the square term and the linear term, take half the coefficient of the linear term and square it, and now we have a completed square. But if I do that, I have to undo that. This is now just a constant. And I now have x plus b over 2 squared, a perfect square, that's what these three terms are, minus a constant. And sometimes that helps me in integration. So here's a problem. I do not have any rules for 3 terms in the denominator. I've got rules for 2 terms. Since this is the quadratic, though, I can complete the square. Okay, half of 4 is 2. Square that is a 4. So if I added a 4 with the x squared plus 4, that's a perfect square. But if I add a 4, I've got to subtract the 4. So this ends up giving me, right, x squared minus 4x plus 4, perfect square. X minus 2 squared. And minus 4 plus 7, that's 3. So I now have this x minus 2 squared plus 3 squared. I now have a square function, a function squared, plus a number. And since I have a function squared plus a number, that fits u squared plus a squared. That's arctan. So the square root of 3 squared is my a. X minus 2 is my u. So this is 1 over a, arctan of u over a plus c, and we have evaluated the integral. by completing the square. By completing the square. Find the area. Now here's a function. And function happens to look like this. Going from x equals 3 halves to x equals 9 halves, so that's going to be these lines. So the area under the curve is this area right here. And we found out that area under the curve is integral. So the integral from 3 halves to 9/4, first value to the second value, of the function dx. But again, x squared and 3x, I don't have any rule for the square root of something like that. I have a rule for the square root when we have a function squared and a number squared. So if I would complete the square on this, I can come up with the result. And I will write this up completely for you so you can see it. But the point is, completing this square is one of those techniques that we need to have in order to work with integration. So here are the 20 integration formulas that we have so far. And when we do integration, okay, we need to look at what's under the integral and try to match it to one of these. By rewriting, by use substitution, we only have 2 techniques. Okay? Rewrite to match one of these rules, or use substitution to match one of these rules. And that's really what we will jump off of in Calc 2. We will start right here. We will start with these integrals and work with them. And then we're going to give some more techniques in Calc 2 that enable us to do integration. Okay? Able to do integration. So to end this section, I want you to look at 2 problems here. Here are 3 integrals. dx, x is square root of x squared minus 1. X dx is square root of x squared minus 1. And the square root dx, the square root of x squared minus 1. Now from a math point of view, C is the least complicated. I mean, they're all pain in an x. But the only thing we have is the square root of x squared minus 1. Here we have an x in the numerator. Here we have an x in the denominator. So these 2 are more complex mathematically than this one. But C is the one I can't do right now. If I look here, this is a square root. We look at the rules. We only have 2 rules with square roots in them. Number 20 and number 18. But this is u squared minus a number squared. We've got x squared minus a number squared. So this turns to be arcsecant, because we have u is x, a is 1, the derivative of x is dx, and so we have u square root of u squared minus 1 du, which is our arcsecant. We can do that one. This one, it can't be the same as that, so this is not arcsecant, so it can't be done with that. I only have 2 rules with square roots under it, so that means it's not going to work with that. So now my problem is this x squared minus 1. So if I let that be u, then the du is going to be 2x dx. And I now have du over u. Sorry, I have du over u to the minus 1/2. So I've got x squared minus 1 to the minus 1/2. The derivative of x squared minus 1 is 2x dx. Adding that 2, I need to have 1/2 out there. And I can do that integral. But the one that's the least complicated, I can't do. Same thing here. Of these 3, this is the least complex, natural log of x dx. And I won't be able to know how to do that integral until I get to Calc 2, the second chapter we do in Calc 2. Right? And we'll learn how to do something called integration by parts, and then I can do that. But I can do both of these by use substitution. Because if I let u be the natural log of x, du is dx over x. So this is just du over u, and we can do it. If I let u be the natural log of x, dx over x is the du. So I can do this one also by power rule, but I can't do the last one. So integration, we don't have enough rules to be able to do all integration. Should be able to take the derivative of just about any function we give you, because that was the emphasis of Calc 1, derivatives. Integrals, we can do some, but we only have two techniques: matching these rules exactly or use substitution. And that's where we basically end up. We got one more section, and it sort of combines everything together, so we'll look at that one more section next